So today we're happy to have a seminar with Anastasia Sofronova on top-down lower bounds for depth-4 circuits, the last seminar of this autumn semester. So without further ado, Anastasia, please, the floor is yours.
Thank you, and thank you for inviting me. So today we're going to be discussing some lower bounds for depth-4 circuits. And let me start. This is joint work with Mika Göös, Artur, Riazanov, and Dmitry Sokolov. And let me start from like the very beginning. We'll start very slowly from just the definitions of what the circuits are. And let me start from like just the general Boolean circuits. So this is a computational model that computes Boolean functions. You have directed acyclic graph here, and in the vertices of this graph, you have Boolean connectives, and or not. And there are sources of this graph where you have Boolean variables, and there is a sink which computes like the overall value of the function. So the fun thing about this model is that if you take just a random Boolean function on n variables, it's going to be really hard for circuits in terms of size, like 2 to the n over n, something like that. So almost all Boolean functions are like really hard, but we don't know any explicit hard examples. Meaning that we cannot take any particular Boolean function and prove that it is hard in terms of size for the circuit. And by the way, the size is just the number of vertices in this graph. And the best explicit lower bound that there is for general Boolean circuits is of order like 3.1 n, so linear, while ideally we would like something exponential. But there are more restricted classes of circuits for which we can actually prove some exponential lower bounds, though they are not as good as we'd like them to be. But this is better than nothing. So yeah, people study, for example, constant depth circuits. Here, instead of just directed acyclic graph, we have a layered tree. And in each layer, you have either only AND connectives or only OR connectives, and the layers interchange. And we also require that the negations can be seen only at the bottom with the variables. So yeah, the variables are like at the bottom of the tree in the sources again, and the root of the tree is this sink that computes the value of the function. So for this model, there are some exponential lower bounds in terms of size of order 2 to the n to the epsilon. Yeah, I was supposed to also write a little bit on the slide, but since I couldn't get my tablet to connect, we'll have to, just deal with that. Anyway.
We'll somehow manage.
We'll somehow manage, yes. Yes. So if we would actually have some strong exponential lower bounds for this constant depth model, like order 2 to the n, we would get something non-trivial for the general circuits as well. So these constant depth thingies, they're interesting in their own right. So they have tons of connection to other areas of complexity theory, but like in circuit complexity, this is also like a stepping stone towards this general circuit lower bounds. Yeah, so this is one of the reasons to study them too. And so I said that we'll be discussing some lower bounds. But before we do that, let me give you some more intuition about what is the power of these computational models and how weaker constant depth circuits are compared to the general circuit. So let's start as a warm-up with some upper bounds. So for example, general circuits can efficiently compute a parity function. So I have some picture here, which computes the parity of two variables. I hope I drew this right. Yeah. And it's easy to scale that to n variables too. you just need to like stack these things, stack these modules, but you will need a logarithmic depth for that, where by depth I mean like the longest path from the variables to the sink of our deck. But anyway, it's easy to compute parity in the general case, but what can we do by constant depth circuits? What is our best strategy for the parity function? And I know it's not that easy to make a Zoom talk more interactive, but let's just try just for this slide. So what is the best we can do? For example, by depth-2 circuits. So it's just CNF or DNF. How do we compute parity as efficiently as we can? Any ideas?
So for CNF, you will just get the exponentially many clauses that rule out even parities, right? And
Yes,
that's the best we can do.
True. Yes, that's true. So yes, for CNF or DNF, you kind of list, for DNF case, you list all the one inputs. So you're just saying that your input is one of the one inputs of parity. And for CNF, as Jakob said, we kind of write down the statement that our input is different from every zero input in some sense. So this is indeed the best we can do. It's not like super hard to prove this. So now that we know how to do depth-2, what can we do for larger depth? Let me just tell you right away. So for larger depth, starting from depth-3, we can do kind of the recursive strategy. We split our inputs into blocks and let these blocks be of size root n, and there is root n of them. And I just want to try every possible combination of values in the blocks such that they give us the right parity of the whole string. So I iterate over all of these values in the blocks. And for each block, I can kind of compute if the variables in the block give me the right value with CNF or DNF, so like with depth-2. And you can also view this as like, so I have these blocks, I can see them as meta variables in some sense. So I build CNF or DNF on them. And then each block I can also compute with CNF or DNF. So that would be like depth-2 plus 2, depth-4, but I can also just choose whether I'm computing a block with CNF or DNF to just so the two middle layers would collapse. So this gives us 2 to the root n in depth-3. And more generally, for depth-D trees, for depth-D circuits, we get the lower bound, the upper bound, 2 to the n to this 1 over d minus 1 with this recursive strategy. And there are some constants in the exponent, which I am not writing here. There are some constants, but we don't care that much. And it is the best we can do, in fact, for parity. And how can we understand that? So how can we prove a lower bound for parity for constant depth circuit? Well, there are several options of how to prove lower bounds for constant depth circuits. Let me give you 2. First one being random restrictions. So I have a picture here. The idea is that you have your constant depth circuit of not such a big size. So you can apply a random restriction and do it in such a way that after applying this random restriction and killing some of the variables in the bottom, you're able to collapse 2 bottom layers into 1. So you're reducing your depth by 1. You can do this again and again and again until you get a trivial circuit. And if your function is not a constant at this point, like it's not a trivial one, then this is a contradiction with the assumption of small size of the circuit. And there is this other option, polynomial approximation. Here, the idea is that, again, using a circuit of small size and small depth, you can build an approximation of the Boolean function by a small degree polynomial. So you can do it inductively. You're looking at your tree, and if for all of the children nodes in the tree you have the approximating polynomials, you can somehow construct the approximating polynomial for its parent. So these methods kind of analyze our tree of the circuit starting from the bottom and going up. At least for random restrictions, it is so. For polynomial approximation, it is a debatable question somehow, but you can certainly view this as a bottom-up technique. And there is this third option of how we can prove lower bounds, which is more like a cluster of techniques. It is something less defined, I guess, than these random restrictions and polynomial approximation. But this is called like a top-down approach. And these proofs are usually more combinatorial in their nature, and they're very similar to what people do in communication complexity. So why do we need this third option when we have these first two? Why are they not good enough for us? The first reason that I've listed here is that, well, top-down proofs are usually more combinatorial, and this is somehow something more which is more close to the heart of computer scientists usually. By the way, I didn't tell you what exactly do I mean by top-down, but like this is something that analyzes the circuit starting from the top of the tree and going to the bottom of the tree. And on the next slide, I will also give you a picture to explain the general scheme of that. But anyway, it's more combinatorial usually. But the main reason I think for studying top-down is the second bullet point. It's that we really, really, really need some new techniques in circuit complexity. So we have these two very powerful tools, random restrictions, polynomial approximation, and so they are really powerful, and they already gave some really nice results in terms of circuit lower bounds. But they're also, so one thing about these techniques is that they do prove a circuit lower bound, but they're also exhibiting some properties of the functions that in principle are stronger than just a circuit lower bound. Like, for example, for polynomial approximation, you're also learning something about a Fourier spectrum. And it seems like, so these techniques gave us the most of what they could to this moment. And if we really want some new results in circuit complexity, we really, really need some new techniques also. Because like proving circuit lower bounds is really hard. And except for these three things, there's also like Ryan-Willison's theorem, which doesn't quite fall down into one of these three categories. But apart from that, these three things are like almost everything that we can do. And I hope to persuade you that it's worth to study the top-down techniques. At least it's not fully explored yet. And there are no barriers for it to be able to prove any lower bound that's true. I hope to say a few things about this too a little bit later. And the third reason here is that there are things that we know how to prove top-down that we don't know how to prove bottom-up. Anyway,
Will you say what this is, or we don't need to know?
Oh yes, there is a reference. It's a very mysterious paper in which I always find something new when I reread it. But the result is a separation of Artur Merlin and Merlin Artur with oracles. Yeah, and it's top down.
Okay, thanks.
Okay, so there is like a long line of work on these top-down techniques in communication complexity, as I mentioned, but in particular also on depth-3 circuits. So why depth-3 in particular, will you ask? Well, it just so magically happens that all of the techniques only worked for depth-3. So that's a downside, yeah. And I think we mentioned about 15 references on depth-3 in a paper, and all of them kind of just stopped working magically after depth-3. So what I want to mention here is this result by Hosted, Yukno, and Pudlak. It's top-down lower bound for depth-3 circuits for parity and majority functions. Now, lower bounds for parity and majority were already known at this time by bottom-up techniques, but this is quantitatively better, this top-down approach. So it gave a better constant in the exponent, I think. And also it was like just this short, easy to read, and again, combinatorial proof. And yeah, so the downside was that it only worked for depth-3. So these guys posed the question whether these techniques can be extended for depth-4 and, well, eventually full constant depth. And this had been open since that time. And among the attempts to solve this, I want to mention also this result by Mayer and Victorson. So their main theorem is information theory statement, and I will tell you about it in a bit. But they also use this to reprove this depth-3 result for parity using these information theory techniques. Okay, so our result is this top-down lower bound for depth-4 at last for parity function, and this lower bound is almost optimal. The loss is this little O of 1 in the exponent. Okay, so now let me explain you a little bit about how do these top-down approaches look like. And then we can talk about the technique itself. Like, I know this is like supposed to be not the technical part of the talk, but the technique is the main feature of our results, so I will talk about it anyway, but in like more abstract sense, I guess. But let's look at the top-down technique, like the general scheme for it. So we have our constant depth circuit. It's a tree, and it correctly computes some Boolean function, or so we think that it correctly computes some Boolean function. In other words, this means that the stop gate separates zeros of functions of the function from the ones of the function correctly. And now, without the loss of generality, let us assume that the stop gate is an OR gate. What does this mean? Suppose that it gives 0 on some of the inputs. Well, this means that all of the subcircuits in the next layer of the tree, they also give 0 on this input, just for this OR gate to be computed correctly. So let's pick a subcircuit in the next layer. It still correctly computes all of the zeros of the function, and it also correctly computes some chunk of ones of the function, because like union of ones of all of these subcircuits should give us the ones of the function, like the whole space of ones, again for the OR gate at the top to be computing correctly. So when I pick a subcircuit in the next layer, this means that I am picking some chunk of ones, and I'm preserving my zeros. And if I choose to take the next step down the circuit, I'm choosing a subcircuit of depth 1 less in the next layer. Then I'm saving my chunk of ones that I had, and I'm picking a chunk of zeros. So a top-down technique essentially is just a walk down the circuit, a walk down the tree, and I'm maintaining during this walk a set of inputs that is separated by the current subcircuit. And at some point, I arrive at some subcircuit and some set of zeros and ones about which I can somewhat trivially say, okay, but this subcircuit absolutely cannot separate these zeros from these ones. So this is a contradiction with our assumption that the circuit computed this function correctly. So this is how we should prove a lower bound. And let's take a look at how this works for depth 3. So I want to sketch out the proof that was in Hoste-Tewkne-Pudlak, and then using that, say a few words about Mayer-Victorson result, and then we will see why did this not extend to depth 4 right away? What are the challenges for depth 4? And how do we handle them? So let's take a look at depth 3 first. So we have our depth 3 circuit. It's a tree. It's of depth 3. And I want to prove a lower bound of the order 2 to the n to the epsilon. Now we know that epsilon is actually 1/2, but just for the sake of simplicity, we say that everything is n to the epsilon in the scope of this talk. So the fan-in of the OR gate at the top is no more than 2 to the n to the epsilon. And let me make this first step down the circuit, as I've explained on the previous slide. This corresponds to me picking a chunk of 1 inputs, and I just want to pick the biggest chunk that I have. I can always pick a chunk of size 2 to the n minus n to the epsilon, because I have some restrictions on the fan-in. Okay, so now we are at depth 2 circuit, and it is a CNF. And I also want to say that it's not super hard to restrict the width of the CNF to the logarithm of the size of the circuit. So it's a K-CNF, and K is n to the epsilon again. And now looking at the CNF of restricted width, I want to say that it absolutely cannot separate the whole set of zeros of parity from this really, really big chunk of ones.
I just got curious. Sorry, Anastasia. This restriction on the K, what do you do? I can set a constant fraction of the variables to get the clause width down, or do I do something else? Or
so you can do that, which kind of takes a little bit from this claim that it's strictly a top-down proof, but you can also just say that this CNF, or rather every clauses of this CNF that we're interested in should actually accept or reject quite a big chunk of inputs too. So the width should be no more than something.
Okay. Mm-hmm. Thanks.
Okay, so I want to say that this CNF of restricted width cannot do this. And I want to say this by telling you exactly which point is the one that will make an error. This special point is called a K-limit. And the idea behind a K-limit is that no K variables can distinguish this point from this chunk of ones that we picked. What do I mean by that? So I'm taking this point, my K-limit, and I'm looking at any K variables inside this, at any K indices inside this Boolean string. For example, these green ones. And then I will be able to find a point in my chunk of ones, this light blue set, such that I have the same values in these indices. So like these green ones, yes. And maybe I want to look at some other k indices, this lavender ones. It's lavender, I guess. Well, the other color that's not green. And then I will be able to find maybe some other point in the chunk of ones that I have that has the same values in these indices. So, and this is true like for every k indices in my k limit. And so now I am claiming that any CNF that accepts this light blue bubble on the one side should also accept the k limit. And why is that? Well, any clause of my CNF should give 1 on every point on the chunk of ones that I have. Well, let's take a look at our k limit. And at any clause in my CNF, it has k variables. Well, no more than k variables. For example, again, these green ones on the picture. And I know that there is a point in the light blue set that has just the same values in these variables. So on the point from the light blue set, this clause should give 1. So on k limit, this clause also gives 1. Like, it's a little bit hard to explain without the writing on the slide, but I hope pictures make up for it. Anyway, the idea of a k limit is that KCNF cannot distinguish this point from this light blue set. And what's funny is that it is also a complete notion in the sense that if none of the points on the purple side where zeros are, if none of these points are a k limit, then for each point there is some clause that distinguishes it from the chunk of ones that we have. So we can just build our CNF from these clauses. The takeaway from this slide is that I'm able to exhibit the point where we make an error, and it is a k limit, and it is defined like this. So no k variables can distinguish the point from the set. Okay, but how do we find this mysterious point? Hostet Yukne Pudlak do this with sunflowers, which is this combinatorial structure about which I will talk in the second part of the talk, I guess, because we'll need this too. And Mayer Winderson did this with unpredictability. So what's unpredictability? Suppose we have some distribution on Boolean strings. This big X is a distribution. And these Boolean strings are of size n. They have n bits. And suppose I sample some string from this distribution. And I also require this distribution to have quite large entropy. Then, so I've sampled this string, but I'm not allowed to look at the string itself. Instead, I'm asked to guess some bit in it, like ith bit. So it's here in the picture too. So I want to guess some bit. I can't look at the string, but I can make some queries to the string. Not too much though. I can query up to q indices, and q, as everything, is n to the epsilon. And of course, I'm not allowed to query the bit itself. Otherwise, this would be not interesting. But I am allowed to query anything else in the string as long as I'm not querying too much bits. So, for example, I'm querying these green ones. So after that, I want to be able to predict this question mark here. And So what does it mean if after these queries, I am able to tell exactly what's hiding behind this question mark, 0 or 1? This means that in X, in the support of my distribution, with like this green part of the string, I can see only one option behind this question mark. I either can see 0 there with these green bits in the string, or I can see 1 there. And so there's just like one option among the two that I can see in the support of my distribution. So the result of Mayer and Victorson is that actually most bits are unpredictable with respect to small certificates. So the setting here is that I sample my X from the distribution with this high entropy. And after that, I sample the bit that I'm guessing at random too, just uniformly at random. And after I do that, with high probability, I cannot predict this bit like at all with any queries, even if I'm allowed to make the queries non-deterministic. What does this mean? Like after I've sampled X and the bit that I'm guessing, if there is at least one certificate in the string, if there is at least one choice of my queries that will help me to determine this question mark, I will go for this best choice. And the theorem of Mayer and Victorson says, well, with high probability, there is no such choice. So this actually helps to generate k-limits. Let me explain how to do that. So this is probably the most difficult, the most technical slide in the talk, but let's go through it anyway. Or at least try it. I will tell after we go through the slide what's the takeaway message from this. So we have our chunk of ones. It's really big. So if we consider a uniform distribution on this chunk, it has large entropy. So we can apply our unpredictability and say that, well, actually with high probability, but it's enough if you find at least one string and one choice of bit in it, which is unpredictable. So I've chosen some string X and I've chosen some bit, and like I just put 0 in there, but it doesn't really matter. But suppose it's 0. Let me now flip this bit. So I'm just changing this bit. Everything else is as it was in X. But by flipping this bit, I am changing the parity. So I'm getting some point in the zeros of parity. And I want to claim that this point Y is actually a k-limit. And why is that? Well, by definition, a k-limit is something that we cannot distinguish by querying just few coordinates, k-coordinates. Let's just query any coordinates in Y. If I'm querying the coordinates that do not intersect with this flipped bit, they are just the same as in X. So by looking at this part in Y, I cannot tell that it's not X, for example, or like anyway, that it's not a point from the light blue side. But suppose we're asking also the flipped bit, which is different from X. But we knew that this bit is unpredictable in X, and what this means is that if I'm looking at any part of X, which is small enough and doesn't intersect with this bit, I will be able to see like the same values that I'm querying and also the other value of the bit in these light blue set. So in particular, I will be able to see the substring in Y that we're querying, like this part that is like in X, and this flipped bit 1, thanks to unpredictability. Because otherwise, this part that we're querying that doesn't include the flip bit, this would be a certificate in X for this 0 bit. Okay, Anyway, if this was too fast or too much, it's fine. But the idea is that using this unpredictability statement, I am able to get a k-limit by just flipping one bit in some string in the chunk of ones that we have. This is the most important about this slide. Okay, so let's try to do depth-4 now. Now that we know something about k-limits and something about unpredictability and like the general scheme for top-down. Very well. Now we have the depth-4 circuit. It's a tree, and as we know that k-limit is a complete notion, we still need to find it when we get to depth-2 subcircuit. But now it's happening after 2 steps. So yeah, here in the picture, the top gate that I have is an AND gate. So when I'm taking a step down the circuit, it corresponds to me picking a chunk of zeros. And then I'm taking the next step, it corresponds to me picking a chunk of ones. So now when we arrive at a CNF, a K-CNF, we have the picture like here on the left. So we have some bubble of zeros and some bubble of ones. And we need to find a K-limit in zeros for ones with respect to these ones. Now, for now, the only way we know exactly how to find a k-limit, well, there are sunflowers too, but what I've told you is unpredictability. So let's just try the most naive attempt to do this. Why don't we apply the unpredictability again? Like these bubbles are quite large, or at least I can choose them quite large. So they surely have big entropy, and we can surely apply unpredictability. But what do we get after we do this? Well, we get this picture. Surely this light blue bubble on the left can be made large. And surely there is a string in which there is an unpredictable bit. But after I do the flip, there is no guarantee that I will end in the part of zeros that I'm interested in. I can land quite far from there. So this is really not what we want. And I want to make one step further in explaining this problem and say that it's not only that we don't know how to use this one bit flip. It's not only that we don't know how to use unpredictability in this case for generating k-limits. It's just if we pick these sets not very accurately, there can be no k-limits in the zeros for once. And let me give you a very silly example. Suppose I just care about the size of the sets. Suppose that at each step, at each of the 2 steps, I'm just picking the biggest chunk that I can. What do I get? Well, I can get this. So suppose that the biggest chunk on the first step was the part of the 0 inputs with just the fixed first bit. Suppose it fixed to 0. And then for the second step, suppose that the biggest chunk was the part of 1 inputs with the first fixed bit 1. So these sets are really, really large. These are just like half of the inputs. And at the same time, they are very easy to distinguish. You need to just look at one bit. And surely there can be no k-limit in this chunk of zeros for this chunk of ones. So we need to do something better. The idea is, so for the first step, there is not like something much cleverer that I can do than just picking the biggest chunk. I'm saying that the first step should be the same anyway, intuitively, because there is not like too much mutual structure. So when I'm just making the first step that I need to preserve, so it's fine if I just take the biggest chunk for the first step, but then I need to preserve some mutual structure. So the question is how to make a second step down the circuit. And the general idea is that we need to find the inputs that still make the problem hard. We need to find something that is called mirror set, inputs that are still hard to distinguish from this bubble of zeros that we've already chosen. So I want to determine what these inputs are. And then for the second step, I want to focus on these inputs. I want to salvage as much of them as I can. So that's like the general idea of how we should overcome these depth-4 challenges, or how we should accurately do these two steps. And so here's...
And just to ask, sorry, I understand we're still like at the intuitive level, but did you say that like the first step you can just go for the biggest set? You're not worrying about
it's not a
because in
super
your
formal
counter
statement.
Example, okay. I mean,
yes.
like so you're saying, yeah, I guess would you like how would you find the mirror set in your previous example? Or like
here.
Yeah.
So I think that
there would be another better light blue set if you just had thought about your mirror sets carefully, is what you're saying.
Yes, something like that. I don't think I can explain how to choose this properly for this simple example without appealing to the technical parts.
Yeah, okay.
But
no,
yes,
I'm just
the idea
trying to get a
is that,
feel for.
Yeah, the idea is that like after we make this first step and we know that the first bit is 0, we should actually not care about this part where the first input bit is 1. We should actually already know that this is not the part that's making our problem hard. So we should discard it and focus on the other branches.
Okay, makes sense.
Okay,
makes sense.
So here I want to also make somewhat of an informal note about mirror sets. I do not want to delve into this too much, but so there is this Hirahara paper on depth-3, which has some discussion on, well, mirror sets in some sense. And basically the statement is that, well, suppose we're doing our top-down proof or whatever, the circuit playing against us is solving a covering problem. So like when it goes from the one layer to the next one, we need to cover by subcircuits the chunk of inputs that we have on one side. So it's a covering problem under some conditions. And by duality of linear programs, to prove a lower bound against that is somewhat the same as exhibiting a hard distribution. A hard distribution on inputs, which is hard, like so hard that we cannot solve correctly by a subcircuit, even a certain measure of it. So this is exactly what we do here with mirror sets. You can view a mirror set as a hard distribution on input in some sense. And then I want to pick, again, just the biggest chunk of the mirror set. Okay, this is also something that was supposed to persuade you that top-down techniques are worth studying. But this is somewhat of an informal note. Yeah. Anyway, the question is, how do we find such mirror set and how do we exhibit a K-limit after? This is the technical part. And about that, I will talk in the second part of the talk. But the two techniques that we use are robust sunflowers and block unpredictability. And this is our generalization of Mayer and Victorson result. Yeah, that's it, I think. And let me just go over some open questions. first one is like really obvious. We would like to get this some larger depth. Yeah. Can we do this for depth 5? Can we do this for depth 6? Can we do this for eventually on all constant depth? Like
do
at some
you get
point,
anything for depth 5, or is like this completely? Is it still like this mirror set thingy breaks down completely after depth 4, or?
Kind of, yes. Like the point where we need to find the mirror set, it's kind of important that we still have the whole set of ones. I hope to be able to show this to you in the second part, but yeah, no depth 5 so far, which is really funny in some sense. But anyway, one can also take a look at some other models of computation, slightly different. For example, constant depth with XOR gates at the bottom. It would be particularly interesting to prove something for inner product. Because this is like a weaker problem, somewhat of a necessary step towards rigidity over bounds. And then one could also try to reprove bottom-up results with some top-down techniques, because we really need to develop new techniques in circuit complexity. And there's also one more which isn't listed here. Maybe the top-down approaches could be used to prove stronger lower bounds for constant depth circuits. This is also like a big open problem. Well, this certainly wouldn't be parity because we have an upper bound, but for something else. Yeah. I guess that's it for the first part. So yeah, if you have any questions, please ask.
Thank you so much, Anastasia. I'm clapping silently here on behalf of everybody listening. Good. So yeah, time for questions. We certainly have. Oh, there's a clap emoji also. Okay, great. So I'm going to participate. To get us started, like more top-down proofs. What's your favorite one or two lower bounds for which you'd like to see a top-down approach? Any particular thing you want to mention?
Yeah, let me think actually about this. Well, I don't know. Maybe just start with doing this for majority. I don't know. Well, we've done this for parity. What about majority? What about I don't know, affine dispersers? Something like that.
Fair enough. Any other questions or comments at this point? I'm looking at the chat also. I don't see anything there. So if there are no questions, then we'll take a break. So we're back after the break, and now we're hoping that Anastasia will walk us through the promised second technical part. So Anastasia, over to you again.
Thank you. So what I expect we'll be able to do during the second part is basically I will tell you the whole proof. It's not really long, it's quite short. So I think we'll be able to cover it all with the exception of two lemmas. Like we'll do this modular two lemmas. I mentioned robust sunflowers and block unpredictability to you. And basically one of the lemmas says that we can do robust sunflowers, and the second one says that we can do block unpredictability. So we will just see how these pieces help us to get the proof. And
those you can just use without modification, or you need to tinker with them, or they're already there for you?
I will formulate the lemmas. So we'll see how these pieces come together. But I don't really want to do the lemmas itself. First, because we'll probably won't have time. And the second is, I think these parts are a little bit too technical, even for the technical part.
Yeah,
because like you need to do some calculations to prove these lemmas, and I think as any mathematician, I don't really like to do anything with numbers, so we'll just skip to the pictures mostly.
Sounds good.
Yes. Okay, so let me just remind you what we've done in the first part and what is our general strategy. So, okay, we need to make 2 steps down the circuit and then to find a k-limit. And I've already told you that for the first step, I want to just go with the peak of the largest set again. So like this part will be just the largest set. And then I want to find some mirror set. And then I want to make the second step picking the largest part of the mirror set, which will be this, and then we'll find a k-limit. So I want to start unpacking with this general plan, actually from the last point here, from finding a k-limit. Because so far we know this bit unpredictability. Let me just repeat it to you again. So we know how to generate k-limits using unpredictability of 1 bit. Right, so we have x here, example with some unpredictable bit. And if we flip an unpredictable bit and get into the target set at the same point, like this y would need to be here. So if we're able to do that, to do the flip and get into the target set, then we have ourselves a k-limit, right? And I've already mentioned that we don't really know how to get into the target set with just 1 bit flip. It's just very restricting. So what I propose to do is let's flip several bits. This gives us more freedom. Still no guarantee that we will land into the target set, but we have more chances of doing this. So let me draw a picture of how this would look like. So I have x, and I have some other string y. So here's x, and I want to flip several bits now. Let me just draw them all zeros. Maybe here they're all ones. So if I could do these flips with several bits, I would give myself more flexibility in reaching this target set. But to do this, we would need some kind of block unpredictability for several bits. So let me try to define it now. This is a definition from Mir and Victorson. They also had some kind of block unpredictability with slightly worse parameters. Okay, so block unpredictability, what it is. Suppose we have some subset of Boolean strings of length n. I've told you about distributions, and I was discussing unpredictability, but just for simplicity, let's just imagine a set of Boolean strings with uniform distribution on it. In some sense, that's hardest case, I guess, where we have these large entropy requirement. Anyway, we have the set of strings, and we also have some blocks of bits. So just subsets of indices in the string of size r. So I have some subset of indices, and I say that a certificate for such a subset, a certificate for R, is a pair where Q is also a subset of indices, and A is value in this indices. And let me draw a picture right away. X, a string, and here I have R, and here I have Q. And in this Q, the values are A. So this is a certificate for that. If just looking at this part, I can exclude something from the supported this. So this means that there exists some B such that for every X in my set, if I see this part here, then I know that this is certainly not equal to B. So for one-bit unpredictability, a certificate helps us to exclude a possibility of a bit being something, like we excluded 0 or we excluded 1 from our options. Here, we also exclude something, at least one string from the like 2 to the size of R possibilities. Okay. So what we would like to have here is a statement of the same sort as for bit unpredictability, something like with high probability for random string X from our set X, and for random R, a subset of indices of size R. No certificates for R in X. So again, the setting is we generate a random string, and then we generate a random block of indices. And then we want to say that with high probability, we cannot say anything about this block, even if we're allowed to look at everything else in the string, as long as the set we're looking at is not too large. No small certificates. Yeah, this is important.
So even if Q is like everything else, you still cannot
Q needs
say
to be
anything.
Small. Q needs to be
Q
small.
needs to be small. Okay, what
Yes,
the bound
yes.
is? No small.
Everything
okay,
is
yes.
n to the epsilon.
Okay.
So yeah, just
so should I
just
think of R as R and Q
yes.
is roughly the same size?
Yes. More or less, yes. So the size of R is roughly n to the epsilon, and the size of Q is roughly n to the epsilon. I will formulate the formal statement of the lemma with all of the parameters, and we can see the ranges for this. And yes, the size of X should be something like that too. This is important. But before I formulate the lemma, let me just show you how to get a K-limit from block unpredictability. So I have some pictures prepared here. Okay, suppose we have some string X in which this part is unpredictable. I'm saying that I can flip any bits in this part. Like maybe I'm not flipping all of these green bits, but maybe I'm just flipping like here and here and here, some of them, doesn't matter. But I get some other string Y with some of these green bits flipped, and like here something is flipped, and here the rest is as in X. And I know that this part was unpredictable in X. I'm saying that if after that I landed into my target set somehow, then this is a win for us. This Y should be a K-limit. For the same reasons as for one bit, actually. Let's look at any K coordinates in Y. And I just want to say, just let me include this flipped set in these k coordinates anyway, maybe for free. Maybe I'm asking for k coordinates here, and I'm also allowing to ask this for free. This just gives more power to a circuit. Very well. So I'm looking at any coordinates in Y. I know that this part in X was not a certificate for that. So if I'm just seeing this part of X, I don't know what's happening here at all. Like I cannot exclude even one string from the support of this green part. In particular, this means that I will have some other string X prime in my set of X's, such that here we have the same values as an X, but here we have anything we want at all. Like, for example, the same bits as in Y. Does this make sense? Well, I hope that it does. Because this means exactly that we can query any k coordinates in Y. We won't be able to distinguish it from the set of X's. So in particular, we can flip anything in the unpredictable block and get ourselves scaling. Now let me go back here, maybe yeah, here. And instead of that, let me just write down the actual statement of the lemma for block unpredictability that we have. So, okay, X is a set of Boolean strings, and the size of X is greater than 2 to the n minus k, for example, right? And then I want to say that R is a block of indices size R. And then with high probability, let me just actually write the probability down. So the probability over X drawn uniform from X and R drawn uniform from that X contains size Q certificate where R is less than and maybe to that power. Yep, that's it. That's the statement. So if we look at the parameters, you can kind of see that this is one of the places where 1/3 in the lower bound comes from. Like you can say that K, the loss in size is n to the 1/3, and then a size of certificate that we're asking for is n to the 1/3, and then the size of block that we want to, or rather don't want to be able to predict is also the same. So then you get this probability as some constant. But in general, like it's enough to just have the parameters such that this is still like a non-trivial bound. Okay. So basically, to apply this lemma, all we need is to have our chunk of inputs large enough. So this need to be quite big. So this is what we need to look after, that after like finding the mirror set and taking the biggest chunk out of mirror set, we still have quite large set. And now we have more freedom in flipping the bits, which is good. But as I've written here, we still need to reach the target set. Even if we have more freedom in flipping the bits, this is still a challenge. So in particular, what this tells us, if we want to be able to reach the target set with some bit flip in here, and I've already told you that the size of this is the size of this is something like n to the 1/3. In particular, this tells us that we need to be within appropriate Hamming distance from the target set. So let me now try to make the first attempt in defining a mirror set, which will fail immediately, but we will be able to correct. So my first attempt will take into consideration this Hamming distance observations. And what I want to do is I want to consider points here, like a point X here, that has a dense Hamming sphere around it with respect to the set Y. So I want to have a lot of points from Y in the sphere around this point. And this is what is written here. So I'm interested in the points such that if I have my Hamming ball intersected with Y, I have that this is quite dense. The set at this point is quite dense in my Hamming ball. So this is the size of the set of points from Y that get into the Hamming ball. And this is the size of the Hamming ball. And this is the density of Y in the whole Boolean cube. And I'm giving it some slack with this 1/2. So then I want to apply, for example, Markov inequality or something like this, and to use this a little bit of slack that I have to say that actually M prime that I've defined here would be roughly equal to in size. The size of M prime is roughly equal to the size of Y. In fact, M prime, the size of M prime should be at least like 1/2 of the size of Y. So does this make sense up to this point? Is the definition of M prime clear? Do we believe that it is large if I define it like that?
Yeah, so I'm trying to, let's see. So
Yeah, M is also n to the epsilon. I mean, this is M, the radius of the Hamming balls. Let me just draw it right here. Radius and the epsilon.
So I feel I'm a little bit lost. So if we just take one step back, so we're focusing on this. We've taken 2 steps down in the circuit already, and now we're focusing on this AND gate. And X is making this KCNF evaluate to true.
Okay, I think I've skipped the important part. Okay, let me just get back a little bit.
Or maybe I missed the important part. Although you
no.
said it.
I think I just didn't mention what we're doing right now, which is like really important. Okay, so far I've explained the block unpredictability, which is supposed to help us right here.
Yeah, so actually I had a stupid question about that as well. I was trying to understand this block predictability. I was sort of thinking that somehow if you had this block unpredictability for blocks that are roughly the size of the clauses in the KCNF, I might be interested in. If I have a lot of block unpredictability, then that might help me to work on a single clause and flip it to true to, flip it within true and false. And because of unpredictability, nothing happens with the other clauses in the CNF. Am I sort of, is this relevant at all, or am I like totally in the wrong direction?
No, I think it is a little bit relevant. This depends on which layer of the circuit do you want to stop. So, in some sense, so if I'm able to like argue how to make the step here, for example, so I do not want to stop at the level where I need to find the k-limit. I want to stop here at the level of the clauses, for example, right? So here I have the clause. So in some sense, here you need something which is even weaker than unpredictability to say that the circuit makes an error. So, okay, this is a clause. So this part would be what, splitting zero inputs. So you would need to have on one side of your inputs either zeros or ones, depends on whether you have clause or a term. You would just need to have two inputs with different values in these variables, for example. So if you're able to exhibit that at this level, then this is also a win.
Okay, but we're working one level above.
Yes, because like to do this at the level of clauses, you need to make also the third step, like to explain how to do the third step. These things, like I'm sure you can rephrase finding a k-limit in these terms, because like this reformulation that I have something at the level of clause that gets me an error also sounds like a complete one. So I'm pretty sure you would be able to somehow go back and forth from the k-limit thing and this. But yeah.
Okay, but so where are we? We started with like so we have now we're looking at, we have an AND gate at the output without loss of duality, and then at the like the next to top layer we're just picking the OR gate with the largest like inverse image of 1. So
this is what I
that was the first step.
Incidentally, I think. Okay, so like we know what we want to use to find the k-limit here, and now knowing what I want to use here, I want to tackle with this. I want to find a mirror set now. And then to pick the biggest chunk of the mirror set as I make in the second step. So here, this is a little bit misleading picture. Let me, I don't know, maybe erase that with half of the circuit, but you get the idea. So we are actually here now. So now we're here, we want to define the mirror set and then make the second step. And then to use our unpredictability to find the k-limit. That's the plan.
Okay, and what do we know about this OR gate now with respect to these different blue circles there? Have we found the dark blue?
Yes. So okay, let me also make this picture a little bit more up to date. So far, we've made the second step, so we've split it the set of zeros, and now we still have the whole set
right,
of
I had
ones.
that wrong. So you're picking the largest set of you picked
Of
the largest
zeros?
set of zeros. I had it wrong before,
Yes.
right? So yeah, sorry.
Mhm.
Okay, and
That's
so okay, and we took one step down, and it's a really large set of zeros, and okay, and we know that that gate, yeah, has to be correct on anything I feed it from the one set. It has to be correct, is what you're saying. That's why you've shaded all of it. Yes?
Yes, exactly. Exactly. So yeah, we need to know which chunk of ones to pick now as we're making the second step. So we want to define the mirror set and somehow deal with that now. So instead of this whole subset, this whole set of ones, I just want to focus on the hardest one in some sense. And so goes my attempt to define the mirror set. And so far, I propose just to take the axes on this side that have dense hemispheres with respect to the set Y, the target set that we want to end up with. The intuition behind this is that, like, after we do the second step, we want to exhibit a K-limit by doing a block flip. And this requires us to be within a certain Hamming distance. So, yeah.
So we're now picking x's that are fairly close to the y set on the other side. Okay, good. Thank you.
Yes. Yes. And quite close, meaning that they have lots of points from y inside the hemisphere of the appropriate radius.
Yes.
Yes. So, yes, this set that I defined here and prime centers of dense spheres, it's quite large because I've allowed here some slack on denseness. But now I want to say that actually we have a problem with this definition, and we've already seen this problem in the first part. So let me get back to the silly example. Okay, suppose at the first step I'm picking this set again. Nothing prevents me from doing this. Suppose it's the largest one for the first step. And now I want to say that my definition doesn't rule out these points. Why? Because actually, if I take a point from here, the sphere around it will be quite dense. But at the same time, let me just wait. So I have some x, and I have first bit fixed. And here we just have a subcube, right? So this whole thing is just a subcube with one bit fixed. And any point from y looks the same, but with the first bit fixed to 0. Here, anything we want. Okay. So what we wanted to do is to find the K-limit is to do some flip inside unpredictable bits. Well, this set is large, and it certainly has a lot of unpredictability. In fact, any subset of bits that doesn't intersect with the first one is unpredictable. Like whatever else we ask in the string, it's unpredictable if it doesn't intersect with the first bit. But if it does, it's predictable. So anything that has this first bit is predictable. but any flip from X to Y should involve the first bit. So we cannot get from X to Y by just flipping something here in unpredictable bits. So I've kind of rephrased the problem that we had in the very beginning in terms of this like unpredictability and what we want from unpredictability and these flips. So this is something that our strategy has to notice for us to succeed. Okay, does this make sense?
It does make sense, yes.
Great, perfect. What I want to say now is that, well, we can fix our first attempt. And let me just say what exactly do we want to avoid this bad situation. Suppose we have some input X, and from which we want to flip to reach the target set. So we have some good flips from this input, and let me call the family of good flips A. So what we need for our strategy to work is a statement like this. I want to be able to find a good flip inside the unpredictable set. So I know that for most X's, most choices of blocks of bits are unpredictable. So maybe let me just sample the block uniformly at random of some size. Here I have some parameter P, which will be so that the size of the block is n to the 1/3 eventually. So I know that if I sample this block randomly, uniformly at random, it will be unpredictable with high probability. And now I want to say that with high probability, actually, I will have a good flip inside this block. So there will be some flip which is good and which lies inside the block. And this probability is high. So again, what I would like to do is maybe sample some X. Let me just go back here. What I want to do when I find my mirror set, suppose I found it already, suppose I've defined it. What I want to do is to be able to sample maybe a random point here, and then sample a random block of coordinates, and then have that two things occur with high probability. First, this block is unpredictable, and second, we have a good flip inside it. And this is enough for us to succeed in finding a k-limit.
And this good flip condition is what failed before?
Yes, exactly. So here, any good flip, again, contains the first bit. So it doesn't lie inside unpredictable block with high probability. So yeah. So like when we sample a block at random, it will not contain a first bit with some probability, right? But then with some quite high probability. But then every good flip will contain this first bit. So this condition fails for this example.
Mm-hmm.
So it would be enough for us to succeed if we just define a mirror set of X's in a way that this condition is true. Well, it just so happens that this is something very well known and very well studied. This is robust sunflowers. So let me just write this down. So a family of sets with this property is called P epsilon satisfying. Or more generally, let me use another letter, maybe B is sunflower if the family of like I mean, here there also should be parameters with which it is a robust sunflower. Probably P and epsilon. So in other words, what we need is a robust sunflower with an empty kernel, where a kernel is just the intersection of all sets in the family. So I've just said that these are robust sunflowers, but in fact, as we need it with an empty kernel, it's enough for us to think about this definition, that any family of sets with this property is P epsilon satisfying. So then it just turns out that, so here's a lonely picture of what we can do, how to fix our failed attempt. So we started our attempt with looking at the centers of dense spheres. And the problem would be roughly if the flips from here to the target set are too structured. Like, for example, if we see some difference bits appear too often. So I'm saying what we can do is we can actually move a center of the sphere a little bit to make this family of flips more spread. So let me now formulate the lemma about that. Okay. Okay, so what do I want to say about this? Suppose we have an X that the hemisphere around X intersected with Y is quite dense. So what we had was like this threshold. Then there exists some X prime. This is X, this is X prime. Some X prime with the right parity. What parity do we need? Probably once. There exists a new center of the sphere with the right parity, such that first, a distance between X and X prime is not super big. Maybe there probably should be something in the exponent, but let me just stop on m here.
Poly
It's not
m?
super.
Poly. So some kind of poly m, you know, m to the delta for some delta is what you're saying. Is that right? Yeah.
Something like that. Probably.
Okay.
Probably should look something like maybe plus little o1 minus little o1. Something like that, but like of order m to the point where we're concerned.
Mm-hmm.
So the distance is not too large. And then when we're looking at this set, and we're looking at the difference between this set and x prime, then this family is P epsilon satisfying, where I will define P in a moment. Where P is just so we would get the normal sizes of the set that we want. P will be like m over n. So that in this definition, we will get R of size m. Okay, so that's the lemma. The idea is that we're able to move the center of the sphere with the right parity, the distance not too large, and we're making the family of the flips around it P epsilon satisfying, which is what we want. So when we're considering which bits we have to change to get from x prime to some points in this sphere, this family of flips is quite well spread, in the sense that a random block of bits will very likely contain at least one of these flips. And the intuition about how to prove this is that maybe the problem with X was that we see some bits appearing in the flips too often. Like with high probability, we would need to flip something in particular to get to this part. As in our bad example, maybe we always needed to flip the first bit. Well, in this case, nothing to do about this. Let's just fix these bits. So let me draw what I want to say, just to give you some intuition about how this lemma is proved. Okay, so I have X, and maybe these bits are too likely to be flipped to get something good, right? So maybe I have 0, 0, 0 here, and maybe in this Y's, I'd be likely to see 1, 1, 1 here. So for our new center, let me just forcefully put 1, 1, 1 here. I will maybe need to flip something else to give x prime right parity, but this will be just one bit changed also. So what I want to say is just after I fix the maximal set of bits that appear too often in the flips, I'm good. Because of its maximality, I won't have anything else too likely. And I also just reduced distance from x prime to most of these points. And also just because when I'm moving this point over here, I'm kind of increasing density of the set y around this point compared to this point. So I won't have to fix too many bits in this way. So this is rather informal, but I just wanted to give you at least some intuition of how this is proved, because I think this looks even more mysterious than the block unpredictability things. But the procedure of how to get this new center of the sphere is quite simple. If you see some bits appear too often, maybe that's the sign what they really should be. And this actually fixes our problem right here. So now a procedure would be, we're looking at the set of ones, and we have dense spheres now around any point in one input. But now I know that, so yeah, here's X here. But I know that in each of these bit flips, I see the first bit. So maybe let me just say that I'm getting my X prime by forcefully fixing this first bit to 0. So I'm eliminating this part completely. I'm always fixing my first bit to 0. And I am left with just this part as my mirror set.
But here it's kind of important that you had all the ones, right?
Yes, exactly. Here it's really important that I have all the ones. So this is one of the places that's preventing this to be a depth-5 lower bound. This is kind of why we currently have it only for depth-4. Because yes, here when I move the centers, it's really, really important that I only have to ensure the right parity at the center. And otherwise it can be any point. Yes, exactly. Okay, so this is actually all that we need for the proof. And let me just repeat the plan, expanded now, knowing everything that we know. And let me just do this voices inside the circuit right here in the picture, just to explain what's happening. Okay, so I'm standing here at the root of my tree, and I'm making the first step over here in this subcircuit, and I'm picking the largest set of zeros for the first step. So this goes away. It goes away. And I only have some bubble here, but it's quite a big one. So this is of size 2 to the n minus n to the epsilon. Now I want to handle the mirror set. I am currently here in the circuit. Okay, I am considering Hamming spheres dense in Y. So far, I don't care about the parity. Maybe it's like, it's really hard to draw Hamming spheres, then this distance is not actually corresponding to the picture, but like, let's say it's a sphere. And this is a sphere. And maybe this is a sphere also. You get the idea. So I'm considering Hamming spheres that have quite a lot of points from Y. And then I want to move the centers to make the flips inside this sphere well spread and to also have the right parity. So I'm moving the centers and I'm ensuring my well spreadness condition and also the right parity. So yeah, I have the new centers here, and this is like here. So this part is well spread around that. Okay, let me just get rid of these ugly spheres and say that now I have my mirror set on this part. So I have the mirror set, M, and it is also quite large. It is also of order the size of Y, roughly that. So now I want to make the second step down the circuit. Over here in the C. And what I'm doing right now is I want to salvage as much of the centers of the sphere as I can. So basically, maybe I'm losing some centers of the spheres here, but I still have some. Let me just redraw this. Okay, so I have a smaller bubble right here, and it's of size 2 to the n maybe minus 2 n to the epsilon. And now I am ready to find a k-limit here. K-limit. Right. And how do I do this? I can actually take any center of the sphere that I have here. And then I can do this. I'm taking this. Oh no, I cannot take any center of the sphere. I need this to be a point where most of the blocks are unpredictable, but this is true for most of the points. Let me just draw this again. So this is X, and I'm choosing a random block of bits R. The size of R is roughly n to the epsilon. With high probability, this random block is unpredictable, or it's unpredictable. And also with the high probability, there is a good flip inside. So I can also look at X as the center of the sphere. And what's happening inside the sphere is really well spread. So with high probability, I will also have like this point, Y, such that X minus Y, or rather the ones in X minus Y. So the difference bits, X minus Y is in R. So then I just have to flip these bits inside R to get to Y. I'm getting here with some block flip, and this Y is a k-limit now. And this is everything that we need to say that, okay, this is the point where we make an error. A CNF that correctly computes this should also give 1 on that. So this is all. That's it for the proof. Modulo the 2 lemmas, this one, and this one about unpredictability. But other than that, this is how it works. Yeah. Let me go to the last picture. Yeah. So any questions?
So you said one thing that would be nice to do is majority. So where are we using parity here? Like why is it so important that we're dealing with the parity function?
So here's the thing. It's really important here when we're moving the centers that we just have to flip one more bit to get the right parity. Because if we're flipping a lot of bits, after we already got the spreadness, the denseness condition, we might ruin it. And this is also something that's crucial. That's like the barrier for depth-5. But I don't know, maybe the majority is easier. We haven't really tried yet to solve this problem for majority.
Interesting. Any other questions or comments?
Yes, I have a question. Can you hear me?
We can hear you well.
Yes, I can hear you.
So my question is you mentioned that you make use of this advanced sunflower lemma. So what if I replace that advanced version by the vanilla primitive version? Does it give you anything, or the parameter doesn't work out?
I have no idea, actually. I have no idea, because the way we've done this, so we've just wrote down this condition, and then we found out that what we need is actually a robust sunflower. Like, even the first draft of the text, it wasn't like in these terms. Yeah, so I don't know. Robust sunflower is just something that popped up by itself. But it's an interesting question, yeah. Thank you.
Any other questions or comments before we thank Anastasia again? Just to say that the pictures were very helpful and very, I mean, yeah, so this is I think the proof by picture is like really helpful here, because it's like, it's
I would hope so, yes, because this this K-limit and unpredictability thing is they're not, they do not sit well when you see them for the first time. Yeah.
No, I think I'll have to read the paper carefully to understand all the details, but this certainly helped a lot. So if there are no further questions, let's thank Anastasia again for the seminar, and thank you so much.
Thank you.